Welcome to Intro to Houdini. This course is designed for new users who want to learn Houdini to create visual effects. We're going to cover only the parts that are needed in order to create cool simulations like explosions, disintegrations, and really any type of effect that you can think of. You will find that Houdini really has no limits when it comes to VFX. We will start with the absolute basics such as navigation and basic tools, and slowly uncover more and more complex concepts until we finally reach simulations. Now, I can't promise that this single course will make you an expert in VFX, but I can promise you that it will set you on the right path to becoming one. With that being said, let's get started. So here we are inside Houdini, and at first glance all of this might be a little bit intimidating, I will agree. There's really a lot of buttons up here at the top, and we have a lot of windows that we can cycle through, so it's super easy to get overwhelmed right as you start using Houdini. Now let me put your heart to rest and say that we only really need 3 windows here. We need our scene view, which is essentially our viewport. We need our OBJ window where we place all of our objects, and over here we need our parameter window where we change different settings and parameters for our geometry. All of these other windows, in fact, we don't really need for now. We could just close them, and in fact some of these I never used in my life and I don't even know what they do. So we can only focus on these 3 windows: the scene view, parameters, and OBJ. Over here at the top we have a lot of different buttons. So this whole thing is called the shelf tab, where we can access different kinds of objects and presets. And I just want to say one thing about this: this is completely useless. I almost never use this shelf tab to do anything, and especially as a beginner, this will probably only make things worse for you. So for example, in the simulation tab, if I go to the pyro effects and I want to use this sparse fireball preset, I can click this and I can hit enter to drop it in my scene. And right away we see that we have a lot of objects and with a lot of different parameters and settings, and we don't really know what any of these are. So I can play the simulation and this will work. So we have our simulation here, but we don't really know what any of these things do. So like I said, especially as you're starting out, I would like to suggest you ignore this entire shelf tool. So we don't have to worry about this for now. In fact, we could hide this if we click this little arrow over here, and really we wouldn't be missing anything. So don't worry about the shelf tab for now. Now, just for the sake of working with the defaults, so we have the same layout, I'll reset everything to the default by going over here where it says build, and I can select reload current desktop. And when I click this, it will reset everything to the defaults. So this is a good thing to know, because if by accident you click somewhere and you mess up your entire layout, you can always go back here and just click reload current desktop and it will reset everything to defaults. Now let's drop an object in our scene and see what we get. To do anything and everything in Houdini, you start by pressing tab. This will bring up the tab menu, which contains all the things you can do or create. And if I go to the bottom here where it says all, you can see all of the nodes that we can create. Now, upon seeing this giant list, I don't blame you if your first reaction will be, how the f am I ever going to learn all of these? Again, let me put your heart to rest and say that you will probably not ever going to use maybe 90% of all of these nodes. And this is because not all nodes are created equal. And we will talk more about this later, but in fact most of these nodes are really just different combinations of other lower level nodes. So they're sort of like presets. There are really just a handful of nodes that build up everything else, and those are the nodes that we have to understand and master. But don't worry about this for now, we will talk more about this later. For now, all I want to say is that you don't really need to know most of what these nodes do to get the most out of Houdini. So enough rambling, let's type cube and we will press enter, and we see that we get this nice little gizmo, and we can place our cube anywhere in our scene by just simply left clicking. So a few things happened. We see the cube in the viewport, and now we have a node in our OBJ window, and we also see some settings here in the parameter tab. We also have a transform handle over here, which we can use to move the cube around, and we can also rotate it and do all of the basic stuff. And as I move it around, we can see our values change in the parameter window over here. And I can also adjust these values directly inside this window. So I can directly set the values by typing here. So let's go to uniform scale and let's type 0.5 and press enter. So now our cube is twice as small. If I middle mouse click this value, we can see this little menu appear. And while holding down middle mouse click, I can go left and right to decrease or increase the values. And now these numbers here represent the increments by which we adjust the values. So if I want to be super precise, I can hover over one of these smaller increments, and while my mouse is over them and I'm holding down the middle mouse button, I can go left and right, and we can see that we can make some really subtle changes to our values like so. And if I want to make bigger changes, I can just go to one of these bigger increments and I can use these values as well. Okay, so hopefully this makes sense. We can see that some of these settings have 3 values, and for example the uniform scale only has 1 value. So if I want to change all of the 3 values at the same time, I can hover over the text and I can change it here. So we can see that we are using all of the values at the same time, and this makes a bit more sense for the scale properties here. So for example, I can scale in all axes at the same time. And if I only want to affect one of these values, I can hover over it and change it like so. So now I'm only scaling it on the y-axis. You can also select a value like so and use the scroll wheel to change the value. The default increment here is going to be 0.1, as we can see, and if I hold down Control, we will do increments of 1. And if I hold down Shift, we can do increments of 0.01. So this is pretty handy sometimes actually. But don't worry about this for now. Most people use the middle mouse menu over here to change the values. So for now, I suggest you do the same. Most of the time, you will be adjusting the values here directly inside the parameter window rather than the viewport like so. So try to get used to adjusting values over here in the parameter window. And now to navigate the viewport, we have to select the view tool over here, and we can see that the shortcut for this is going to be escape. And now I can hold left click to orbit around the object. We can use middle mouse button to pan, and we can use right click to zoom in and zoom out. And if I want to go back to our transform handle, we have to make sure that our object is selected, and this is indicated by this yellow outline that the object has. And now we can press enter and we can get our transform handle back. And again, we can use escape, and now we can navigate our scene, press enter, and now we get our transform handle back. Now when I press enter, it's important that our cursor is inside the viewport, so this will be context sensitive. If I were to have the cursor inside the OBJ window and press enter, we can see that this does something else entirely, and we will talk about what happened here in a second, but for now I will just go back to our OBJ level. Another thing to note here is that when you are using the transform handle, you can hold down space, and this will activate the view tool, so now we can navigate our scene, and when I release space, it will bring me back the handle. So now I can adjust things, I can hold down space, move things around, and release space, and I can continue to adjust by using the handle. So this is super handy, and it's something that you should get used to. Let's add another object in our scene. So I will press tab and let's type torus, let's press enter, and let's add this over here. And again, we have our transform tool, and I can either press escape, so I can move my camera, press enter to get it back, or just hold down space and move my camera like so, and then release space. Now I can also press S on my keyboard, and I can select the cube, so now we can see this yellow outline, which means that the cube is now selected, and I can press enter to get my transform handle, and I can move this around, so I can press again S, select my torus, press enter, and then move this around, and hold down space and move my camera around. So let's maybe go ahead, zoom out, and let's just place this torus somewhere else further away from our cube. And let's say that we are working on our cube and we forgot where we placed our torus. I can actually come over here in the OBJ window and I can select the torus. And now in the viewport I can hold down spacebar and press G, and this will frame our camera on the torus now. So this is extremely useful. And I can do the same for the box. I can select this box object over here in the OBJ window, hold down spacebar G, and it will center on our cube. And if I don't have any object selected, so I can just left click inside this empty space over here, and if I center now with spacebar G, it will frame all of the objects in our scene. So this is also pretty handy. So this is pretty much the viewport. So we are at the object level or the object network. In Houdini, we have different networks for what we are trying to do. So if I hold down left click over here, we can see all the different networks that are available to us. So we have image, object, material, stage, task. So really we have a bunch of networks here, but just like the nodes, we don't really have to know all of these right away. In fact, 95% of the time we are only going to be working at the OBJ level. And here is where we actually create all of our effects. And later down the road, we are also going to look into the mat and the out networks. So the mat network is where we create the materials, and most 3D packages have some sort of material window or a materials tab, so this is what this mat network is. And the out network is essentially our render settings window. Again, other 3D apps will have like a window somewhere where you can adjust the render setting. Don't worry about this for now. Like I said, most of the time we will be spending at the OBJ level. So in the OBJ network, we create our objects, and I can hold down Alt and left click drag to duplicate any object, and I can really drag and make a lot of copies of these, and I can move these around, and we can populate our scene like so. Now, this might be a little weird for you if you have used other 3D apps before. You might be used to seeing this, which is our tree view. So if we go here in this OBJ group, we can see all of our objects over here, and we can also access them. We can see that when I select an object here, it also selects it in our viewport. So we can definitely use this to move around, and this is what you might be used to. So this will be sort of like the classic outliner that lists all of the objects in our scene. But really, you will be better off if you get used to working with this object network view, which is pretty much the default for Houdini. And you will also find that you really have a lot of way to organize your nodes. So for example, if I hold down Shift and grab a few of these nodes, I can hold down A and drag horizontally to align them horizontally, or I can grab these and I can hold down A and drag vertically to align them like so, and I can grab these and I can also align them as well, and I can grab these and I can create a network box, and we can really keep things organized like so. So maybe this will be our primary effects. We can rename them here, and I can do another network box over here, and this will be our secondary. So you can really keep things organized if you want, and it just takes a little bit of getting used to. So let me get rid of all of these, and I will start with a fresh box, a simple box at the center of our scene, and let's focus on this for a second. Remember earlier when I had my cursor in the object network and pressed enter, and this is what happens. So if I select this box geometry and press enter, we see that we get a slightly different icon for our box geometry, and we also have slightly different parameters here at the top. So now we are inside the box geometry container. So this is actually our geometry. So now for this box geometry, I can increase the axis divisions, for example, and I can set it to a different primitive type, and we can do all sorts of new things here. So we can also see that we are at the OBJ level, and we have this little arrow here that points to box 1. So this is our container. And if I press U on my keyboard, we can go up at the object level. So previously, if I press double click, we can see that now we are at the geometry level over here. Alright, so if I go up, we are back at the object level. We can also see things maybe more clearly if we go in the tree view here, and we can see that we are in the OBJ level, and inside this box 1 container is going to be our box 1 geometry. Now, for example, if I go to the OBJ level, I can rename this to whatever I want. So I can actually rename this to box container. So this will make a little bit more sense. So if I go back to the tree view, our box 1 geometry is going to be in our box container. So let's go back here. So we are at the top level, which is our object level, and double clicking will access our geometry level. And here is where we actually build all of our effects and where we will spend most of our time. So for example, and don't worry about what I'm doing for now, if I press S and I press 2, I can go ahead and I can grab some points around and I can modify the geometry, and we can see that we are starting to build a chain here. Don't worry about this for now, we will come back to this in a second. Let's also append a transform, and I can also use this to move it around. So remember that we are still at the geometry level. So now if I go up, we can still grab this container at the object level, and we can also move this around, and we can see that all of these changes are added on top of the geometry that we modified. So if I go back at the geometry level and on this transform node, I can still move things around, and I can go up and I can move things further here at the geometry level. Now I did all of these things just to say this one thing: you will not usually have to deal with transforms at the object level. So over here, in 99% of the cases, if you want to move the geometry, you will go inside and you will use a transform node and move it over here. So if I go up, all of these transformations will be set to the 000 and the default settings. And on that note, if you want to reset any settings, you can hover over the text, and if you hold down Control and middle mouse click, you will reset them to their defaults. So that's all I'm trying to say here. Whatever effect that you want to create, you will start at the object level, you will press tab and type geo, and you will add this geometry node. So I will press enter and I can rename this. So let's maybe say that I want to create a tornado here. I will rename this to maybe effects_tornado, and then immediately I will go inside and I will start building my chain over here. Now something else happened, and we can see that our original cube became transparent. So for example, if I were to add a new geometry here, so I will hit tab and type torus and press enter, our torus looks like it should, but our cube is transparent. And this is going to be this option over here where it says ghost other objects. So this is the default that Houdini uses. And if I were to switch this to show all objects, now our cube is being drawn as it normally is. Now if I also set this to hide other objects, we no longer see our cube. It will only show what's inside the geometry container that we are currently in. So we are currently inside this FX Tornado geometry container, so we are only seeing the torus. And this is extremely important because while this is saying hide other objects, it is in fact not loading the object at all in our scene. So it's not turning it invisible and working behind the scenes. It is in fact not loading anything from the cube geometry. This means, for example, that if I were to go up, so I'm pressing U, we can see now that when we are at the object level, we automatically see all of the objects. And when I step back inside the box container, we now no longer see our torus. So this is extremely important because if, for example, inside this box container we have a super heavy effect that has millions of points and we want to work on another effect, we can go up and we can create a new geometry container, and when I go inside that new geometry container, we no longer have to deal with the millions of points that are contained within our initial effect. So for example, I could have our effects rain over here, and inside here we will build all of our rain effects. And if I go up, we can now focus on our tornado effects without loading in any of the millions of particles from the rain effects. So this is super useful to just focus on the current effect that you're trying to do without worrying about the other effects slowing down your scene. And at any point you can come back here to this icon and show all objects, and it will load all of the objects that are in your scene. And sometimes this ghost other objects option is useful when mostly placing things around, so you don't have to worry about intersecting geometry and you can really focus on what you're doing with just having an idea of where the objects are in your scene. So it is sometimes useful, but most of the time you will either use show all objects or hide other objects. So let's set this to show all objects and let's go up. So again, at the object level, you will only create this geometry node, you will drop it, rename it to something more meaningful, so FX Fireball, and you will step inside by double clicking, and then here you will actually build your effects at the geometry level. So I'll go ahead and start fresh and delete all of these, and let's do another geometry node, and I will step inside, and you can see that by default this is empty, so I can go ahead and drop down a box. And I will hold down space in G so our camera can focus on this object. One other thing to note here is that the tab menu is different at the geometry level and the object level. So if I press tab over here while at the geometry level, all of these nodes are actually different than what we have at the object level. So it actually happened to me a couple of times when I was first starting out, and I wouldn't be able to find the node that I'm looking at, only to realize that I was actually looking for the node at the object level. So when I press tab here, we have different nodes entirely. So just keep this in mind. If you press tab and look for a node and you don't find it, make sure that you are at the correct level. So let's go back inside our container. So now that we finally got all the boring stuff out the way, we can actually start having some fun, and let's see how we can modify this geometry. Like mentioned earlier, we have different settings that we can play around here, but what we are going to do is add new nodes and link them together. So let's go ahead and I'll press tab and I'll type color, and let's bring out our color node. Let's link it to our box and we will change the color here. Let's maybe use green. Okay, so I changed the color to green, but I don't see it displayed in my viewport. And this is because we have to set the display flag for our color. Currently our display flag is on our box, which is indicated by this blue circle around our box. So we can hover over our color and we can turn on this eye icon, and now we are previewing the result of the color node. So this is how we can change the display flag, and the hotkey for this is going to be R. So if I want to go back to my box, I can select the box, press R, I can select the color and press R, so I can preview the result of the color. So similarly, we can now drop down a transform node. So let's drop this down. We will link it, and we are now going to preview this transform node by pressing Alt after selecting it, and I can go ahead and modify the translate and the uniform scale and all of our options that we have. And this whole operation here, which I did, which is dropping down a node and linking it and setting the display flag to that node. So if I want to do all of this in one go, I can, let's maybe use a new node, so I will type clip. And if I want to directly append it to my chain and set the display flag to it, I can hold down Shift and then press Enter, and we can see now that it's linked to our transform and also has the display flag to this. So we are now starting to build a chain here, and at any point I can go to any of these and I can modify values here. So I can select the color node and I can set this to red, and it will propagate down our chain. I can go back to the transform node and I can press Enter for this because we have handles. It's important to note that not all of the nodes have this handle, but for the transform I can use this to move it around, or I can use my parameter settings over here, and I can even go all the way up to my box and I can change some of the settings here. So I can turn on uniform divisions, I can use all kinds of settings here. You can see also that when I select this box, we have the wireframe for where it started. And this is sometimes pretty useful to know, but if I don't want to see this, I just have to go and select my clip node over here and just preview this. You can also see that this clip also has a different transform handle, so I can use this to see where I'm cutting the geometry, which is essentially what the clip node does. But if, for example, I go to the color, and let's also set the display flag to the color by selecting the node and pressing R. We don't have a handle in the viewport when we press Enter, but we do have these options here at the top, so I can use these as well. So I can set this to blue, and now I can go back to my transform, and then I can go back to my clip. So you can see that I'm selecting the node, pressing R and switching through these, and this will be a lot of what you're going to be doing on a daily basis. So if I hover one of these nodes here, we have some other options that we can try. So after the display flag, the most important one is going to be this bypass node over here. So if I click on this, we can see that now our transform is grayed out and we no longer are applying this transform on our geometry. And the hotkey for this is Q. So if I press Q, I turn it on, and I can disable it by pressing Q again. So this is extremely useful when you are troubleshooting. And for example, if I let's enable the transform back and go to my clip. So this is the end of my chain. Let's say that for some reason this clip isn't working. We can go ahead and quickly check if some of these other nodes are interfering if I turn them on and off by using Q. So super important to know this. And other than that, we have this freeze option over here. This will just mean that when you click this, it says lock. So this means that the geometry is now embedded in the project file. This honestly is not really important for now, so forget about this option. Just for now, I'll disable this, hit OK. And the other option that might be more useful is going to be this template display. And in order to show this, let's maybe do a duplicate of this transform. So I can hold down Alt and drag to create a transform, and you can see that this is automatically linked to where it was. So with this second transform, I can now move this around. And if I preview my clip and I also want to see the results of this transform, I can go to this and turn on this template display, and we can see now the wireframe. And the hotkey for this is E. So if I select this and press E, we no longer have the template flag on. So sometimes this is useful when you are working in larger scenes. You might want to check where other nodes are positioned in your scene. But probably for now you don't really have to worry about this. The most important ones are going to be the display flag, so R and then Q to disable. Now if you want to remove a connection, you can disconnect any two nodes. If I grab a wire and press delete, so you can see now that this is disconnected, so let's reconnect. And you can also, if I grab this transform and I wiggle this, we can see that this gets rid of the connection as well. But really my preferred method is going to be holding down Y, and you can see now that the cursor turns into a scissor. So now while holding Y, I can drag across a wire and cut it like so. So this also is very intuitive and makes a lot of sense, and it's actually pretty fun. So that's how you can disconnect nodes. Now it's important to note that the display flag can only be set on one of these nodes. So if, for example, I select this other transform node and press R, the display flag switches from this initial transform to this second transform one. But if I go up at the object level, I can actually have multiple of these nodes, and all of them can have the display flag set to on. So let's maybe just rearrange these a little bit so we can easily separate them and see what's happening. So for example, I can turn the display flag for this on and off, so I can preview any object if I want, and I can disable all of these or enable them. But when we are inside the geometry level, we can only have the display flag set to one of these. Let's maybe hide other objects here. And this is because when we are at the geometry level, we can only have one single output. Now you might find this a bit annoying until you get used to it, but really it's not as limiting as you might think. It just takes a minute to really get used to this way of working. If you really want to preview multiple nodes at the same time, you would have to use a merge node. So for example, I want to have the clip, the result of this clip and the result of this transform, and merge them. So I can drop down a merge, and I can plug this here, and also I can plug the transform here, and now I can preview this merge node, and I have both of them at the same time. And when I go up, let's set the display flag for this to be on, and now I can see them both here. Let's maybe get rid of these. So now I have both of these also at the object level, but this isn't really what you usually will do. So let's go back here. Let's get rid of this merge node. And what we usually do after we build our chain and we reach the end of our effects, we can drop down a null and we can append this null, and I can rename this to something meaningful like out rain effects. And really you can give this any name you want. Usually people like to use this out prefix whenever we're doing this. So this null doesn't do really anything by itself, it simply points to the end of our chain. So at any point, if I want to go back up here and I want to do some changes, maybe to our box, I can modify this box, and maybe I also want to add some new nodes here. So I can drop down another transform and add it here in between our box and the color and do some changes here. We will have this null that will always point at the end result. So this is super useful when organizing your scene. And this is also very useful when you want to import the geometry into a different container. And this is also something that you'll be doing quite a lot. So for example, if I go up and this is my effects rain, if I want to do a separate container for, let's say, effects splashes, and I step inside, I can build my effects here. So I can drop down a sphere, for example, and we can build our chain again. Let's maybe use a color here and a transform. Now this isn't really what you're going to be doing most of the time, but let's just say that you're building up the chain for the splashes effects, and we need our splashes to communicate somehow with our rain. So if I show all objects here, we need to somehow import this geometry into this separate container. So for this we can use an object merge. So if I drop down an object merge, I can go ahead and I can go here where it says object 1. Let's click on this icon over here. So if I go to the effects rain and collapse this geometry container, we can easily point to our null, which is going to be this out rain effects, and this will be the end of our chain. So we can grab it over here. So I can hide other objects, and now essentially our rain effects geometry is living inside of this container. So this is the base of how you will get multiple effects to interact with each other. So I'll go up and I'll get rid of splashes, and let's go back in our effects rain. So these nodes here that we added, the transform, the clip, the color, these are a specific type of node. Specifically when we are at the geometry level, we are dealing with surface operators, or SOPs for short. And for example, if we were in the out network, so if I go to my out network here and drop a node, so if I press tab and select any of these nodes and I add it here, we are going to be dealing with render operator type nodes, or ROPs for short. And dynamic operators will be DOPs, and so on. So all of these terms simply refer to the type of operation that you're trying to do. They're all essentially still just nodes. So SOPs, ROPs, DOPs, we are dealing with quite a few operator types here. Again, just like the nodes and the networks, we don't really care for most of these. As VFX artists, the ones we care about are going to be SOPs, or surface operators, VOPS, or vector operators, or DOPS, dynamic operators. And then maybe later when we are rendering stuff, we are going to be dealing with render operators or ROPs. But for the most part, we are going to be focusing on these three right here. So think of these as sort of like mini networks. All of these, the SOPs, VOPs, and DOPS, are basically contained within the object network. So they're like smaller sub-networks. So this is pretty important because, again, depending on what we are doing, we are going to have access to different types of nodes. So when we are in the object network and inside the geometry level over here, when I press tab, we are going to have different kinds of nodes. And when we want to create simulations, we are going to be dealing with dynamic operators. So just for now, I'll just create a DOP network. So a dynamic operator network. And when I step inside, don't worry about this for now, we will come back to this in a second. But when I step inside, we see that this changes, the name here changes to dynamics. So now when I press tab, we're going to have different kinds of nodes entirely. Now there is quite a bit of overlap. So for example, some nodes that are available at the surface level, so at the geometry level, are going to be available to us in the dynamic network as well, so in DOPS. So most of the time we're going to be doing similar things that we do in SOPs, we are going to be doing in DOPS. We're going to be using kind of the same nodes, but they're going to be applied in a different way depending on the level that we're at. This will make a little bit more sense in a second, so don't worry about this for now. All we have to understand for now is that all of these are basically sub-levels of our higher levels, so our big networks, OBJ, MAT, and so on. These are smaller levels that exist within those bigger levels. And again, we don't really have to know everything. We are going to be focusing here at the big level. We are going to have OBJ. So OBJ will have SOPs, VOPs, and DOPS, which are the three main levels that we are interested in. So this is pretty much what all of this SOP, ROP, DOP thing means. It simply refers to the type of operation that we're doing. So finally, I can stop calling this the geometry level and call it what it is, which is SOPs. And this is what most people will say as well. They'll say that we're in SOPs, not at the geometry level, even though they're pretty much the same thing. Now that we got all that, we can finally start talking about attributes. And we're actually going to start using Houdini. Attributes are the most important part of Houdini. Your ability to create and modify attributes is the single most important thing that will determine your success as a VFX artist. An attribute, in the simplest terms, is just a piece of information that you can attach to geometry. This attribute, once you create it, will transfer down over to all of the other nodes. So for example, over here in our chain, after our box, let's go ahead and I will drop down an attribute create, and let's create an attribute. Now don't worry about all of these settings for now, we will get to all of these in a second. Let's just give this a name, and I will say name will be driver, and let's just give this a value of 1 over here. Again, we'll cover all of these settings in a second. And another quality of life tip here, if you want to move a node and all of the other nodes that are above that certain node, you can hold down shift and we can see that we drag the box along with it. As opposed to if I wasn't holding shift and just drag this node, it will just single out this node. So hold down shift and it will also move what's above it. And if you hold down control, you can move what's below a certain node. So this is a great tip to keep things organized. So I will just make some room over here. So this is where we create our driver attribute with a value of 1, and to check that this is working, we can go in our geometry spreadsheet, and we can see here we have a list of all of our points, and we have this driver over here with a value of 1 assigned to all of the points. We also see that we have this px, py, and pz, so this is the position, and this is a built-in Houdini attribute, but you don't have to worry about this for now, we will talk about it more later. So we can see that this driver is automatically assigned to all of the points, and in fact you can't have an attribute exist only on certain points. It's either on all of the points or none of the points. If you wanted this driver attribute to only exist on certain points, you would have to separate the geometry in order to do that, but don't worry about this for now. So I want to say a few things about this geometry spreadsheet. When I was first starting out with Houdini and I saw this window, my first reaction was, what the f***? I have to learn Excel to do explosions? So right now, if you also have the same reaction, don't worry about this window. This window is only here to check that your attribute that you created is working. So that's all this is. You won't ever have to know that the point number 60 has a p-value of 0.695 and a driver attribute of 1. It doesn't work like that. I'm only in this window to see that this driver attribute was created and it has a value of 1, because if I look in my viewport, we don't really have any visual indication that this attribute was created. So this is why we have to go in the geometry spreadsheet. So you will be using this quite a lot, but you don't have to worry about this too much. This is only here to troubleshoot and see that your attribute is working and it has the correct value that you assigned it. So anyway, let's go back, and we created this driver attribute, and we can see now that it will go to all of these other nodes below it. So if I go in the geometry spreadsheet, now when we added this color node, we also added another attribute. So color is another attribute, but we see here that this driver is being passed down to all of these other nodes. So when I go and I reach the end here with this null out rain effects, we have our driver with a value of 1 on all of the points. So what we do in Houdini is we use our attributes to drive other attributes. So for example, the color is an attribute, and we can use this driver to affect our color. Now a value of 1 isn't really interesting, so let's see how we can also modify this attribute. After we create our driver over here, and let's go back to our scene view, let's drop down an attribute adjust float, and while we are on this subject with the tab menu open, you can see here that what I typed was add, and f. So this is another quick tip. If you type the first letter or the first two letters, you can find the node that you're looking for more easily. So for example, if I wanted to drop an attribute VOP, I would type ATV and it will pop up on the attribute VOP. But I only typed ATV. So this is just something that you will get used to. So let's go ahead, and I wanted to drop an attribute adjust float. Alright, so let's plug this here after our driver. Now don't worry about what float means, we will get to this in a second, but we can use this node to modify our driver attribute. Now currently this is set to modify our p-scale, so let's switch the name here to our driver. So I will type driver, and I will leave the settings as they are because we will get to these in a second. I want to change this adjustment value tab here. So I want to randomize this driver a little bit. So we will set the pattern type here to a random value, and the operation, let's set this to multiply. And this min and max value will change how much randomness we add to our driver, or rather multiply our driver with. So now if I go back to the geometry spreadsheet, we can see that this driver value is now different for each point. So it will go from a value of, let's see, 0.000, almost 0, to a value of almost 1. So in between we will have all of these random values. And again, this is all the geometry spreadsheet does. It's here to check that your attributes are working and that you are getting the expected result. So to use this driver now in our color, let's go back to our scene view and let's go to color. So remember that we created and adjusted the driver before our color. So now in our color node, we can set this color type to ramp from attribute. And inside the attribute name, let's type driver. Okay, so now we can see that based on this ramp that the color provides, we are going to have some random values in the range from 0 to 1. And we can also go to our geometry spreadsheet and we can see that the color is the same value on all of the three components that it has, and it also matches our driver value. So back in our scene view, now I can adjust the ramp and I can maybe set this black color to red and I can set the white color to blue. And all of these things that we just did here is how Houdini works. So all we are doing in Houdini basically is we are simply adjusting attributes and modifying them. And any given geometry can contain a million attributes, so when we add up a lot of different operations, that's how you end up with really complex effects. But at its core, it's really all just attribute. So hopefully this gave you an idea of how the stuff works. So let's go to our attribute create and let's examine this a bit. So we gave this a name here, driver, but this really could have been anything. I could have named this my vel and everything would have worked. Only now we would have to update all of the other places where we use this attribute. So this attribute adjust float, I would have to go here and type my vel, and also inside the color we would have to type here my vel. Alright, so now everything would update and we would have the expected result. So let's go back here, and this is case sensitive, so if I have a capital V here, you would have to write it in the same way on all of the other places as well. Next we have class, and we can see that the default here is going to be point. So let's see what this means. In Houdini, we can attach an attribute to a geometry either on points, primitives, vertices, or detail. So all of these are quite unique with different use cases, but for us as beginners, the most important one is going to be points. And if you understand how attributes work at the point level, that knowledge is going to transfer over to the other ones as well. And probably maybe 90% of the time we are going to be dealing with point attributes. So think of it like this: a geometry can be just points. So for example, a particle simulation is essentially just points. Now, if you want to do a collapsing building, we are going to need the primitives and vertex as well. So these two are kind of linked to each other. But we are going to be dealing with these two on top of dealing with points as well. So in Houdini, point is king. And this detail thing is something that is also on any given geometry. And I'm not gonna lie, when I first started out, it kind of twisted my brain a little bit trying to understand this. And I think it only makes sense once you see it in action. But for example, let's say that we have a particle simulation and each particle is going at a different speed. Now, if I want to find out what is the fastest speed in that simulation, we would have to store that information on the detail level, because there can only be one value which is the fastest speed basically. So don't worry if this doesn't make any sense for now. First, we have to understand how the attributes work at the point level, and then we can expand on this information. Next, we have type, and we can check this list and see that we can have many different types. Now, in reality, there are more types than this, and here is a list of all of the types. So if you're a nerd and have a background in programming, all of this will be a no-brainer for you, but you don't have to be a programmer to understand all of this. And just like the other stuff, not all types are created equal. In fact, the most important ones are going to be float and vector. Now, we're also going to introduce integer pretty soon, because it comes up a lot. And much later, when we are all grown up, we can talk about metrics as well. But for now, like I said, we can focus on the float and the vector, and just knowing these two can really take us pretty far. So in Houdini, I can go ahead and I will drop down an add node, and I just want to use this to create a simple point at origin. So I will click this plus icon over here and we create a point. And if I move this point around in space, here we are actually modifying the position attribute, which is a vector type. So if I go in the geometry spreadsheet, we can see that this position vector is made up of three components, which are the x, y, and z dimensions. And when I change it here, it will also update in our spreadsheet. And this is how we move points around basically. So a vector will usually have three components, but it can also have two components. So when you are dealing with UVs, for example, you will have two dimensions, only x and y. So it's going to be a vector 2 made out of two components. And when we are dealing much later with quaternions, that's going to be a vector 4, so a vector with 4 dimensions. But we don't have to worry about this. 90% of the time a vector is going to be made out of three components, and that will be enough for us to do a lot of stuff with. Now if I append a transform node to this and I change the uniform scale, we can see that we only have one component here. So this is what's going to be referred to as a float value. So this value here is going to multiply all of our values in each of these components at the same time. As we can see here, we are basically grabbing each of these values and multiplying it by this value that we are setting here. So most of the time we are dealing with float values, which can really be any numbers. It can be something like 5.34, and this differs from an integer type, which can only be a whole number. So it can either be 5 or 6. It can't be 5.45. So the integer is usually used when an attribute can only be a few different values. So for example, if I have a particle simulation and the particles are affected by a force like wind, if I want to disable the wind in the middle of the simulation, I could create an integer attribute wind and set it to 1, and then when I want to disable the wind, I can set it to 0. So it could be either on or off, 1 or 0. It can be something like 0.5, so it's just half on. So I'll go ahead and delete this, and let's do a little bit more practice with attributes. So let's add another type of geometry that Houdini provides, and I will add a platonic solids. Let's press R on this, and I will set this solid type to this dodecahedron option thing, or however you pronounce it, and we will just increase the radius. Let's maybe try a value of 3 over here. And I want to add more geometry to this so we have more points to play around with, so I will do a subdivide. And I'll set this algorithm option here to the last one, which is this open subdiv 1, and I will just increase the depth maybe to a value of 3. So now we have a lot of geometry that we can modify. So remember that the position is also just an attribute that we can modify. So over here I will drop down an attribute adjust vector because the position is a vector type. So let's go ahead and add this. And by default, this is going to look for the v, which is the velocity. We'll get to this in a second. Let's change this to p, which is our position. So it's important that you type this with a capital P. Otherwise, Houdini won't recognize this. And because we are going to adjust the vector, when we go here to the adjustment values, we have this first one here that says adjustment 4, and we have some options here. The default is direction and length, or we can just affect the direction only or the length only. So this is specific for vectors, and let me just quickly illustrate this. Let's just focus on 2 dimensions now, x and y, to make this simpler, but it's essentially the same thing for a 3D vector. So we have a point in space that has a value of 5 on the x-axis and a value of 2 on the y-axis. So here is our point. Now these 2 values can't really exist without an origin. So our origin in this case is going to be 0, 0. And in Houdini, when we are dealing with position, and I go over here to the geometry spreadsheet to check our position, all of these values are based from the center of our scene. So I can press W to go into wireframe mode, and over here where it says 0 and 0, this is where actually all of our position values are originating from. So I'll press W again. Let's go back to our graph. So now we can draw an arrow from the origin to our point to represent this vector. And this arrow will have a direction, so where it points, and also a length, so how far along this arrow will point to. So this will be our length. So for example, we can now have another point that points in the same direction with a value of 2.5 on the x and a value of 1 on the y. So this will be the same direction as our original vector, but this vector will have a smaller length. So really you can think of this length as sort of like the overall scale of the vector. So it's pretty important that we know this early on, because we're going to be doing vector operations in a minute, and we have to know this difference. And just another example, if we have a particle simulation, and for example we follow the position of a point through the entire simulation. So let's say that our point will start over here at frame 1, and at frame 2 it's going to be over here, and at frame 3 it's going to be over here. And let's say that over here we reach frame 10. Let's say that I want to keep this direction in which it's already going, but I just wanted to go faster. So let's say we will want the point to go twice as fast. We would be able to multiply this vector by a value of 2. So we can scale up this vector, and then on the next frame, so on frame 11, our point would be over here instead of where it would have initially gone, so over here. So all of this will make more sense and start to click as we do more stuff. So let's go back now to our attribute adjust vector. So let's keep this at direction and length. Operation will be add, and instead of adjust with constant, let's go ahead and select here noise. Now I just want to say right away that noise is your best friend in Houdini. You will be using noise on a daily basis to modify attributes. So we modified the position of our points, but this isn't looking too great. If we scroll down, we have our noise settings here. So there are a lot of noise types, and we can check all of these are and what they do. So they are going to be quite different from one another. Let's maybe just increase the element size so we can see this better, and maybe also I can add more resolution. So in my subdivide, I'll set this depth to maybe 5. Right, so let's go back, and also if I don't want to preview the wireframe on top of my object, I can press Shift W in the viewport, and now we don't see the wireframe. So let's go back here, and we can see that as I change the noise type, we get really different results. So as you learn Houdini, you are going to learn more about these noise types, so don't worry about this too much for now. I will reset this value by holding down Control and middle mouse clicking. So the default here will be simplex, and we can adjust the element size and the offset. And also we can go down here to animation, and we can also animate this noise. And now if I hit play, finally we have some animation on our screen. So on this note about the play bar, we can see here that we are working with 240 frames, which is essentially 10 seconds, but we are blasting through this entire timeline in maybe like 3 or 4 seconds. So this is because we have to turn on this real-time toggle, so this little watch icon over here. If I turn this on and I go to the first frame and I hit play, now we can see that we are actually previewing this in real time, so at 24 FPS, which is the Houdini default. I don't really know why this option isn't turned on by default. Usually when I start up a new project file, I will just turn this toggle on and I will just keep it on for the entire project. So don't worry about this for now, just turn this on and leave it like that. So let's see how we can actually combine this attribute adjust vector with another attribute. And by itself, this attribute adjust vector is pretty limiting, so the better version here would be to use an attribute noise. So I'll go ahead and delete this and I will drop down an attribute noise and let's use attribute noise vector. So the vector version, let's add this here. And we have pretty much the same settings here. Let's set the vector back to our P. And this will work just like the attribute adjust vector. I can change the element size and the type, and we can also, let's go to the animation and we will turn on animate noise. So it's pretty much the same thing. The only difference with this node is if I go up, we have this blend option over here. So if I turn this on, we can see that we can blend between where our points were originally and where they end up after we apply the noise. So we can either set this value directly ourselves here, or we can go to where it says constant and we can set this to use attribute. So if I click this, now this blend value will be driven by an attribute that's called mask. And really, again, this can be any name. I could name this to driver, and we would just have to make sure that the attribute that we create is named driver. But Houdini by default will give us this name mask, which sounds good to me. So all we have to do now is, before this attribute noise vector, we have to create an attribute mask that will drive our noise. So we can see that this mask has to be a float value, so one single component. So we can use an attribute adjust float to create this attribute. So if I drop this here, let's go to this node and the attribute name will be mask. And by default, this attribute adjust float will create this attribute if we don't have it already. So over here we did an attribute create and then we did our attribute adjust float. But in reality, we didn't really need this attribute create over here. So if I delete this, our attribute adjust float will create this value. So if I go to the end here, we have pretty much what we had earlier. Alright, so let's go back to our attribute adjust float here and work on our mask. And let's press Shift W and also view our wireframe. So if I scroll down here, let's set the type here to maybe line. And I can visualize what this will do for us in the viewport. If I go over here, we can see that after the name, we have this icon over here. So if we toggle this on, we will have a visual indication in the viewport of what's happening. So when I set this type to line, this gave us access to a handle in the viewport. So if I press enter, we see that this is the line that drives this attribute. So basically this point over here will be 0 and then this point over here will be a value of 1, and it's going to give us a smooth gradient over to 1. So it's going to be 0 and then in the middle 0.5, and where it's red it's going to be a value of 1. So this is essentially our mask attribute. And if I no longer want to visualize this, we can click this icon again. And we can also go in our geometry spreadsheet and we can see that we have a mask value that starts from 0 and goes all the way over to 1. So if I check this, we can see it start to increment. So if I go back in my scene view, this will mean that wherever we have a value of 1, our noise will be fully applied, and at 0, none of the noise will be applied, and as a result, we end up with this. So if I press Shift W and check my animation, we have the noise only have full effect where our mask has a value of 1. So this is how we can start combining attributes, and hopefully now you have a better idea of how it all comes together. Now let's do just one more example. We will start with the same platonic solids. We will go all the way up here where we didn't make any modifications, and I will do a poly extrude. And let's see this. So this poly extrude is running over the primitives, and if I increase the distance here, we can see that we push out our polygons. And if I want to operate this over individual polygons, I can go up here and where it says to divide into connected components, we can set this to individual elements. So now we are extruding each polygon separately. Now if I go to the local controls over here, we can map this distance value to an attribute. So we can turn on distance scale, and this Z scale is going to be the attribute that drives this distance. So again, I can create an attribute adjust float, and I can set this to Z scale. And for this I will set the type to random, and we can see that nothing really changed. All of our extrusions now should have had a random value between 0 and 1. And this is because, like I mentioned earlier, our poly extrude operates over the primitives, so it's looking for a primitive attribute. So we can go in our attribute adjust and we can set the class here to be primitive. And now we can see finally that something happened, and we can go ahead and modify these values. And now we have a different distance for each extrusion. So this was just an example to illustrate that this is where the attribute class comes into play. It's pretty important which class you assign the attribute to, but as I said earlier, as beginners, let's just focus on points, and we can see that pretty much it's the same operations here. So the way we modify the values is going to be the same whether it's points or primitives or vertices. But this was just a quick example to demonstrate to you that it does matter what class you assign the attribute to. So we can modify attributes, and we can create different attributes and modify those and combine them. And if I hit tab and type attribute, we can really see all of the different operations that we can do with attributes. So we can see there's really a huge list here. So all we have to do is learn what each of these do, and then we know Houdini, right? Not really. All we really need to know is one single attribute here, which is going to be the attribute VOP. So let's go ahead and let's add this to our scene, and here it is. And this is the single most important node that you have to learn in Houdini. Remember when I said earlier that your success in Houdini will be depending on your ability to manipulate and create attributes? This is what I was talking about, this attribute VOP over here. So all of these nodes, the attribute adjust float, the attribute noise vector, all of these attribute nodes can be recreated inside this attribute VOP. So this is why this node trumps all of the other nodes. Now don't get me wrong, you will still use some of these attribute nodes simply because some of these might take a minute to set up in VOPS, and since Houdini already set them up, there's no reason not to use them. So we can still use all of these, we don't have to create everything in VOPS, but it is important to note that if you want, you can recreate everything in VOPS. So earlier when I said that we are working with surface operators, we are now going to take it one step further and introduce VOPS. So VOPS is referring to vector operators, but really we're not only operating on vectors, we can modify and create any type of attribute, so we can create float attributes, integer attributes, or any other kind. Now this is a huge topic, and I have a separate course dedicated to specifically learning and understanding all the different nodes and operations that you can do in VOPS. But for now, we're only going to look at the basic stuff and see how everything works. So we are going to connect this attribute VOP to our subdivide over here. And let's press R to visualize this, and we will dive inside. So we have these two blocks here, and you can pretty much think of these as inputs and outputs. So on the left, we have our inputs, and on the right, we have our outputs. And if we look closer here, we see a bunch of letters, and some of these letters that are on the inputs you will also find on the outputs. And all of these are Houdini's built-in attributes. So these are attributes that Houdini will understand by default. So for example, this V over here, this will be our velocity. And if we create and modify the velocity in any way, when we use this geometry with this velocity information, and for example we want to create a particle simulation, then Houdini will understand to use this velocity attribute and how to apply it to our particles. So we have these built-in attributes, and some of these are actually global attributes. So for example, the frame here is a global attribute. These are also sometimes referred to as global variables. So this frame over here will return the frame value, and we are currently on frame 76, so this will give us a value of 76, and it is global because no matter what geometry we are operating on, we are still going to be at frame 76. So if we change the geometry and do operations on a different geometry, this will stay the same, and this is why it's a global attribute. So time, time inc, and frame are global attributes. But we don't have to worry about all of this for now. Everything will start to make sense as we start actually doing stuff. But for now, one important thing to notice is that some of these attributes have a different color assigned to them. So green is going to be vector, teal is going to be float, and blue is going to be integer. So like I said earlier, the most important types are going to be vector and float, and sometimes integer. If I look down here, we can see that we have a lot of these blue values, so integer types. But really the most important ones, and the ones that you're going to be working with most, is going to be the ID and the PT num over here. I rarely find myself using the other ones. And then we have these orange values over here, so op input 1, 2 and 3. And if I go up, we see these 4 dots over here on our attribute VOP, and these correspond to each of these op input parameters here. So basically op input 1 is going to be ourselves, so the geometry that we are currently doing operations on. And if I were to plug this polyextrude node over here in the second dot, I would be able to access this geometry from this op input 2. So if I want to interact with this polyextrude geometry in some ways, I would do this from this op input 2, and the same will be if I also want to talk with this geometry over here. I can place it in my third input for our attribute VOP, and I will be able to access it through here. And we will get more into this later, but essentially these orange values here, this is what they represent. So I can go up and like I mentioned earlier, we can hold down Y and we can cut these wires. So we remove the second and third connection, and let's go to our attribute noise vector, and I will disable this blend option for now, and let's try to recreate this in VOPS. So if we examine this for a second, we can see that we are running this over the P attribute, so our position, and we are adding the noise values on top. So we can add, subtract, multiply, whatever, but we are adding. So this is important to note here. So in our attribute VOP, let's switch to this. Let's go inside. So first we have to generate these noise values. So I will search for noise here, and we can see that we have a bunch of types here, but the most basic one and the most common one that you are going to use usually is going to be this turbulent noise. So let's go ahead, let's select this and drop it in our scene, and here it is. Now this by itself, we can see that we have a bunch of inputs over here, and we have an output, which is this noise value. Now we can just plug the result of this noise, so the output of this noise, into our P and expect this to do anything. In fact, we can see that our geometry disappeared. So I'll go ahead and let's remove this connection, and let's take a look here. First of all, this output is going to be a teal color, so this is a float value, and we want to modify the position, which is a vector value. So we have to switch this signature here where it says 1D noise, we have to set this to 3D noise. Now we can see that this noise turned to green, which indicates that it's now a vector. So now if we remember from our attribute noise node, we added the noise values on top of our existing position. So we have to plug our existing position in our output. So now basically we're just taking the position as it is and outputting it without doing any modifications. And now in between we can add our noise. So let's go ahead and drop an add over here. So I'll search for add and press enter, and we will hook this here, and then we can add our noise on top of our position. So if I plug this over here, our geometry moved a little bit, but this isn't really the expected result. And this is because the way the noise works, it needs our position from where to generate these noise values. So we have to plug our position, so the P, in our pause over here, so in the position input for this noise. And now we can see that we are getting a similar result to what we had in our attribute noise node. So if I go to this turbulent noise, now we can play around with the settings, and we can also change the type. So maybe I can use sparse convolution noise, and now this is even more closer to what we had. We can change the amplitude, and we can increase the frequency, and we can pretty much do the same things that we did with our other attribute noise node. Now this by itself isn't really impressive, but what I can do now is I can build on top of this. So we don't actually have to use these sliders to modify values in our noise. I can actually drop a constant, so I will type here constant and drop this. And this constant is just a simple float number. It sounds fancy, but literally it's just a number. So I can use this constant now and plug this in our amp, so our amplitude, and now I can use this constant to modify our amplitude like this. And this can be any number here, it doesn't really go from 0 to 1. I can increase this if I want, or I can even go in the negative values. So still not really impressive, but again I can build on top of this. So just for example, using only the knowledge that we have, I can drop down and add to this constant here, and I can add our original position, and we can see that we start to get some freaky results. So maybe instead of adding, let's see what happens if we do a multiply and we actually multiply our position with this constant. And now if I change the constant, we get a different result, but again, this isn't really useful, but it's just to give you an idea that we can really build a large network here of operations, and we have control at each step. Also, I can modify the noise value output over here, so what we are outputting from this turbulent noise. So I can do an add here, and I can also maybe use the position to add on top of the values that we output. Again, this is just to give you an idea. Let's go ahead and maybe delete all of these and just keep our noise, so what we had originally. And by the way, if you want to reverse the order of the nodes here, if I select this add node and press Shift R, we can see that we switch the input order, so this is really handy. So it's important to note that for add or multiply, the input order doesn't matter, but it does matter, for example, if we want to subtract, or if we want to divide, or if we want to multiply a vector by a float value. But all of this doesn't really matter right now, but it's important to mention this because we are going to be dealing with this, so input order does matter, so be careful how you switch the order here. So let's take it one step further here, and let's say that I want to scale this amplitude of our noise based on the height of our points, so the position of the points on the y dimensions. I forgot to mention this, but if you are in your viewport and you hold down spacebar and press 2, 3 or 4, we can switch through all of the different orthographic views. So we can see that we are in the right view here, and we can go to front with spacebar 3, spacebar 2 will be top, and spacebar 1 will return us to perspective view. So if I hit spacebar 3 and go in the front view, we can see that this is going to be the y and x planes, and we can see that the geometry on the y-axis can roughly fit between a value of -3 over here at the bottom, and at the top it's going to be a +3. I will press W so we can preview the wireframe, so we can see that it's 3 at the top and -3 at the bottom. Okay, so press W again. So we can actually use these values to scale our noise. So we are going to grab our position, and we need to split the position, which is a 3 float vector. We need to have access to each individual dimension. So for this I will use a node called vector to float, and notice that I'm typing the abbreviation, which is VTF, so vector to float. Let's press enter and add this, and now we have 3 values that we can output here, and this is essentially our x, y and z components. So from here we need a second one, which is our y component, and if I just plug this into our amplitude, we get a different result, but this isn't exactly what we want, and this is because we are outputting exactly the values as they are here. So we are going to have an amplitude value at the bottom of -3, and it's going to ramp up increasingly to a value of around +3 at the top. And we have to remap these values to something that are a little bit more useful to us. And to remap values, we can use a fit range node. So let's make some room over here. And after we output our y value, we can do a fit range. And here we can say that our source min is going to be -3, so this will be the lowest value, and our source max is going to be 3, so this will be our highest value. And now we are remapping these values to 0 and 1, so these are the default that Houdini gives us. So this means now essentially that we are going to have an amplitude value of 0 over here, and it's going to ramp up all the way to a value of 1 over here, so where our y position is 3. And we don't really have to use 0 and 1, we can use any values here, so we can see that we start to get some really cool results. Let's maybe just keep this to 0 and 1. So if I go back to this attribute noise vector, if I turn on this blend, and let's go back to our perspective, so hold down spacebar and 1. If I enable this blend with our mask, we see that we did these 2 steps. So first we created a mask attribute, and then we used this to blend our mask. We did this in one simple step in this attribute VOP. So if I go back inside, instead of adjusting the values inside this network, so if instead of adjusting the sliders here, I can expose these values to the upper level. So if I want to expose the destination max here, I can go to the destination max input in our node, and I will middle mouse click, and I can say promote parameter. So now if I press U and go up, if I scroll down here for my attribute VOP, we have this maximum value in destination, and I can use this slider to adjust it at the SOP level. So now when I step back inside, we can expose only the parameters that we need, because most of these values we don't really need to adjust. For example, let's say that I don't want to touch the source min and source max, or I'm not really interested in changing the frequency or the offset of the noise. We can, for example, here, let's say that I only want to change the frequency. I'm not interested in the offset, so I will go ahead and I will middle mouse click on frequency, choose promote parameter, and now I can go up and I will be able to access the frequency from over here. So I can change this at the SOP level now, and I can play around with the maximum destination range as well. So we can choose what parameters we want to expose. And this is pretty much the same thing that these other attributes work. For example, if I step inside, we can see all of the nodes that actually create this attribute noise vector node, and we actually have a few attribute VOPs over here, and we have a bunch of other stuff. And when I go up, we can see exactly the parameters that Houdini exposed for us. And this is the same thing that we are doing over here. We are exposing only the parameters that we need, but now we can keep building on this and really do whatever we want. So we are not really limited to just modifying the noise or scaling it based on our position. We can really do a lot of operations here. So we are in the framework where we can build and expand on our ideas. So this is the power of VOPS and the power of Houdini in general. We are using the low-level nodes, so the primary building blocks, to create and modify attributes in any way we want. So this whole thing that we did here, this exact same process is what I use to build really complex effects. Only obviously a little bit more advanced than this, but not really a lot more advanced than this. Don't imagine that I use hundreds of nodes over here and I build something like this, a huge network like this. Most of the time it's really just gonna be a few nodes. And the reason being that I can pretty much stack a lot of attribute VOPs. So if I go up, I can hold Alt to duplicate the node, and I can attach it to my other node. And we can see that the same operations that we did here got added on top of the geometry that already existed. So in reality, there are really a bunch of nodes like this. And each of these attribute VOPs would do a different thing. So maybe I want to modify the position here, I want to modify the velocity with this one, and I want to do another thing here. And in between these attribute VOPs, there are going to be more regular nodes. So maybe there's going to be a fuse here. And it doesn't matter what this does. The idea that I want to illustrate here is that you don't really have to do everything in just one single attribute VOP. You will usually stack a bunch of these when creating more complex effects. So aside from all of these simple math nodes like add, multiply, divide, there are really a lot of other operations. So for example, for vectors you have cross product, you have dot product. So you will encounter a lot of these and you will start to understand them and get to know them once you actually start using them. So this is why I created the VOP series, where I go over the most used nodes and do quick examples on how to use them. So definitely watch that right after this. Now this might be pretty obvious, but at least as I was starting out, this wasn't very obvious to me. But this whole thing that we are doing here is essentially a for each loop, which means that this action here, all of the operations that we do are really happening per point. Only it's running on all of the points at the same time. And this is how you actually have to conceptualize this. So let's say, for example, that we only want to do certain operations only on the upper half of this geometry. So if I press spacebar 3 and go in my front view, let's say that I want something to happen to all of the points only if their Y position is greater than 0. So I can go ahead and where we split our position vector, we can grab this Y value and we can compare this to a number. So let's drop down a compare node, and we want to say that if the position of the point is greater than, let's say, a value of 0, so the condition here will be greater than. So if it's greater than 0, let's see what this will give us if we plug this bool result over here in our CD. So now we can see that all of the points that are below 0 turn black. And let's go back to our perspective view. So what happens here is that this compare node can only return a value of 0 if the condition is false, and a value of 1 if the condition is true. So on that note, this is why this bool result here is an integer value, because it can either be 0 or 1. It can be 0.5, so like we mentioned earlier, it can be half true. It's either false or true, so 0 and 1. So what this attribute VOP is doing essentially is it's running over all of the points, and if I turn on my point display here to help us visualize this better, it's gonna go on this point over here, and it's going to check if the y position of this point is greater than 0, and then it's going to set it to 1, and it's going to go to the next one, and it's going to check if this y value is bigger than 0, and it's going to set this one, and it's going to do the same thing for all of these. And when it reaches over here on these points, it's going to look on this point, and it's going to do the same thing. It's going to check the y value, and this one will be below 0, so it will set this color to 0. So it's important to think of this attribute VOP like this as operations per point. And it's important to think of it like this because each point will have a unique number. So I can turn on the point number display, and we can see that there's a number attached to each of these points. So this is going to be sort of like the unique identifier of our point. So these values that we see here for each point is going to be this PT num here, so the point number. This is going to be how we can access this value. So this PT num is an integer value that is a unique value for each of the points. So two points can't exist having the same point number. And this PT num is generated automatically no matter what geometry you add. If you have particles or if you have ridges, as long as there's points in the geometry, this PT num will exist. Now this is extremely useful for us because this is how we will be able to identify certain points in our own geometry or from other geometries. Essentially, a lot of the operations that we are going to do is going to rely on this PT num value. So again, this is why it's important to think of these operations as per point operations. Now you don't have to actively think about it like this, you just have to have this in the back of your head somewhere when you are doing stuff over here. Now a common thing that you can do with this PT num is, since this is a unique value for each point, we can use it as a seed to generate a random number between 0 and 1. That's going to be different for each point. So from this PT num, if I drop down a random, now this will output a random value between 0 and 1 for each individual point. So for example, let's go back and let's turn off these point displays. And if I were to add this randomly generated value to our amplitude over here, so after we do our fit, let's drop down and add, and let's add this to our amplitude, and this is what we get. So this will be completely random for each point, as opposed to the noise value. So if I disable this add node for a second, the noise values are also kind of random, but they're not completely random per point. You can see that we have a sort of rhythm for it. So there's a special algorithm that the noise uses to generate these values. They're not completely random like this value that we generate here based on our point number. So this also comes up quite a lot, and this is why I wanted to mention this. So let me just get rid of these. So these are more or less the basics of VOPs. Now the nerd version of the attribute VOP is going to be the attribute wrangle. So if I go up, I will drop down an attribute wrangle. So these look the same. They have the attribute wrangle also has these 4 inputs, and this is because they are essentially the same thing, only in the wrangle we write code over here to do anything and everything. So let's hook my geometry to our attribute wrangle. Let's switch to this, and let's say I want to move this geometry by 2 units on the y dimension. I can say at p.y plus equals 2, and we can see now that our geometry moved upwards by 2 units. So this is how this works. So this is VEX, and this is the programming language that Houdini uses, and you will hear this term get thrown quite a lot in the Houdini sphere. So when you hear someone say VEX, they're really just talking about code like this. If I were to do this operation in VOPS, let's maybe just do another VOP node, so drop an attribute VOP over here. I would have to add to our position, so let's plug the P in our P, and I will drop an add here, and I can create a constant. And by the way, you can also middle mouse click this input, and you can choose to promote this as a parameter, but you can also just turn this into a constant. So this is essentially like dropping a constant and hooking it to our input. So we will add a constant, and let's switch the type here. So this constant can be any type. It doesn't have to be just a simple float, so I will switch this to a 3 floats, and we can see that in parentheses we have vector. And we also have vector. I'm not really sure what the differences is. I usually just use this version, so 3 floats. And I can set the second value here, so our y component I can add 2, and we are pretty much have the same thing. So what we did over here is what we are doing over here with this simple line of code. Now we can see that in VOPS this actually took a couple of steps, and it was probably easier to just write a simple line to do all of this. So there are definitely some cons and pros for each side, but the biggest cons of VEX is that you have to know programming. So you have to be familiar with how code is written and where to add parentheses and not forgetting semicolons and all types of nerd shit. And before I started to learn Houdini, I did have a bit of programming experience, so I was able to pick up VEX pretty easily, but everything you can do in VEX you can do in VOPS. So you don't need to learn programming first in order to use Houdini. Now obviously if you have experience in programming you will be more comfortable using VEX, so that's totally fine. But the main idea here is that if you get good at either of these, the skills will transfer. Because when we are in VOPS, we are still essentially just programming, only this is visual programming. But we still have to know what a vector is, what a float is, how to split a vector, how to use basic math operations, what a cross product is, and so on. So if you get to understand and learn VOPS, you will be able to make the switch to VEX more easily, and it goes the other way around. If you already have experience in programming, or if you are using VEX already, all of the things that you know in VEX will transfer over easily to VOPS. We are essentially doing the same things. Now the harsh reality is that a lot of tutorials, especially older ones, are going to be using VEX. This is the way it's been done for ages, there's nothing we can do about it, but I really prefer doing things in VOPS. In fact, in my day-to-day work, I probably use VOPS around 90% of the time, probably even more. And let me just give you a quick example why. There is a function called findAttributeValue, and we are not really concerned what exactly this does for now. I just want to illustrate something. So if I want to use this function in VEX, I can type findAttributeVal, and we can see that this pops up a menu, so we can select it from here. And when I want to give this the argument, so this is how programming works. If I open parentheses, we have to put these arguments in the parentheses. So if I open the parentheses, we can see that this gives us this enormous giant text window over here that tells us what arguments are and what they do and how to use them and what order and all the stuff that we need. So we need a geometry. This will be 0, which is our cells. Then we are going to need I don't know, something like our point number, and then we need to specify what kind of type we want. So we want float. Now this isn't really how the findAttributeValue function works, but this is to say that if I get lost or I somehow don't place these arguments in order, I have to select my function here and press F1 and go to the documentation and check that I follow the structure that it gives us correctly. So you will constantly have to search up the functions, like even if you use them a million times, you can still easily mess things up. Or whenever you haven't used a function for a while, it's very easy to forget, especially the order in which these arguments have to be placed, so that matters a lot. And when I first started using Houdini professionally, I was actually using a lot of VEX, and simply because all of the tutorials were using VEX, so I used VEX myself. And increasingly I found myself using the attribute VOPS more and more. So then one day I tried to use this findAttributeVal in the VOPS version. So when you go inside attribute VOPS and you search for findAttributeValue, we can see that we have this nice little window, and all of the information that you need to feed into this in order for this to work is all exposed for us right over here. So we can point this at the right geometry, for example, and we can specify if this is a primitive point attribute or whatever, and we can specify what's the name of the attribute that we are looking for. So let's say that we are looking for attribute class, and then we can insert the search value over here. And we can also specify if this is a string or integer attribute, and then we can just use the result from here in the rest of our operation. So this for me is honestly a lot more comfortable. and it simply makes my life easier. Every time I had to use this function in VEX, I would have to look up the documentation and see what I was doing wrong and where I was messing up the arguments, and I was getting annoyed and I was wasting a lot of time just doing that every time. Now that could be me just being a f***ing idiot, so it's gonna be up to you to decide which path you want to follow, but especially as a beginner with no programming experience, and I know a lot of you come from Cinema 4D or Blender and there's no way you wrote a line of code in your life. I know you. VOPS will be the way to go. Houdini is pretty damn difficult to understand as it is, and on top of this now you also have to learn how to write code. That's a little bit too much. Now I gotta give credit where credit is due. For example, some things are kind of easier in VEX. So for example, if I want to do a simple if statement, if I want to do it in VOPS and I drop an if block, it's gonna give me this thing, which is a little weird, and we have to plug a lot of stuff in here to make this work, whereas in VEX this is a very simple one line if, and in parentheses we type position y is greater than 0, then at py plus equals 5. So just an example, if your y value is greater than 0, let's add 5 units to that. So it's pretty clean in VEX, and it can get a little messy in VOPS. So also a for loop for each loop here, this can get a little messy, but the point is here that you can still do them in VOPS without really knowing how to write code. And this won't be the limiting factor as you're starting out fresh as a beginner. And after you get a good grasp on VOPS, try to learn a bit of VEX. And if you know VOPS already, it should be pretty easy to learn VEX as well. So excuse my rant, we are going to be using VOPS. All my latest courses and my future ones will mostly use VOPS as well, and we don't have to worry about VEX that much for now. So how does all of this tie together to create simulations? So we know SOPs, where we create and modify geometry. We know VOPs, which we can use to create and modify attributes. And finally, we can start talking about the thing that makes everything work, which is DOPs, so dynamic operators. And this will be the final ingredient to understanding Houdini. So I'll go ahead and actually let's just get rid of everything and start with a simple box and drop this down. And if I want to use this box to generate particles and have them move and create a simulation, we would have to do this in a DOP network. So I'm not gonna hook this right away to the box, but if I drop down a DOP network, here it is, and when I step inside, we see that we have this output and we are in the dynamics context. So now we are in DOPs. I just wanted to create this DOP network first because for particles we can use a POP net. So I will plug this box inside a POP network, and if I preview this result, we see that we are pretty much spawning particles every second. So I'm saying particle, but really it's just a point. So in Houdini, a particle is a simple point, and this differs from other 3D applications where a particle is something different, but in Houdini it's very simple. A particle is just a point. And this POP network, it's really just a DOP network, so we can see this title here where it says DOP network. It says POP network basically because it's a preset of a DOP network. So if I go inside, we have a bunch of nodes already laid out for us, but we are still in the dynamics context, so this is essentially just a DOP net. And we can recognize this output node that we had in the DOP network as well. So we have a bunch of nodes here, and we will get to these in a second, but first let's go up and let's create a velocity attribute so we also give these particles some movement. So before we introduce our PopNet, so right after our box, let's go ahead and create this velocity attribute with the attribute VOP. So let's drop down an attribute VOP, and I can rename this to set V, so set velocity, and if I step inside, I will just create a simple constant. Alright, and let's use a float vector because the velocity is a vector, and let's say that I just want to push these particles 1 unit on the X direction. So I will set this first value here to 1, and I'll leave this as 0, 0. So this is just a vector that points in the X direction, and if I plug this in my V, I can now check it in the geometry spreadsheet and see that we have this velocity information. And now if I go back and I go into my POP network, if I reset the simulation, now we can see that our particles are moving in this direction that we assign to our vector, like so. So this is just to quickly demonstrate how it all comes together. And now, for example, I can introduce some noise to this vector. So if I go up, I can generate a noise based on our position. So I will type here turbulent noise. Let's use a 3D noise because we are working with velocity. And I will simply add this on top of the value that I already have. And now if I reset the simulation and check this out, we can see that our particles also have a little bit of randomness to them. So this is how it all comes into play. So let's go up and let's go back inside our DOP network and let's examine these nodes. We have a pop object over here, a pop source to the right, a VOPS Solver, and our output. And really this merge doesn't do anything. We can get rid of this for now. So we have basically these 4 nodes. Now it's pretty important to get familiar with this structure because this is more or less the same way all of the other simulations are built. So this pop object is simply a container which holds all of our points, and this pop source will look at our geometry and use it to scatter points each frame. So this is why the points start on the surface of our cube. So we source in the points over here, and then our pop object will hold all of these points, and then they get solved by this VOPS Solver. And this is the engine that's telling the particles how they should move at each frame. And then finally we have this output, and this output node is just here to make sure that what we are exporting at the SOP level, so when I go up, what we see here at the SOP level is actually what the output is pointing to. So in this case, our VOPS Solver. So no matter what my display flag is set to, when I go up a level, it will point to this VOPS Solver because of the output. And this works the same way on the SOP level as well. So for example, if I have a box and the display flag is set to this box, but I also have a torus in the scene and we have an output attached to this torus, now even if my display flag is on the box, when I go up, we are actually seeing the torus. So this is what the output node is doing. It simply points to the object that we want to export at the higher level. So this is actually pretty useful sometime at the SOP level as well. But inside a DOP network, we are always going to have this output. So like I said, this is just here to point to the correct node that we want to export. Now this solver here, this VOPS Solver, is actually the heart or the engine of the simulation. This is what separates essentially DOPs from the SOPs. And there are different types of solvers. So for example, we have the flip solver for water simulations, we have pyro solver for smoke simulations, we have rigid body solver for rigids, so for collapsing buildings and stuff like that. We have volume solver for cloth simulation, and I think these are really the main ones that we use most of the time. And these solvers all have different rules and algorithms and calculations that tell the points or the geometry or the volumes how to actually move. So this is why a flip solver will make your particles move like water, and this is how the pyro solver knows how to advect the volumes, because each of these use different, like I said, calculations and algorithms. And if you really want, you can also modify these calculations that are happening under the hood. So for example, if I grab the flip solver and I right click and choose allow editing of contents, when I step inside here, we can see a huge network. So if I press Ctrl B, I can actually maximize any window in Houdini. So we can see how everything is done at every step of the way, and we have access to all of these. So all of these nodes together are what's actually telling the flip solver how to solve our particles, and we can see that it's really a huge network and you won't probably ever have to deal with this. So let's go up and press Ctrl B. We can see that Houdini gives us the main settings that we have to worry about. So in all of these tabs, these are the settings that you will adjust to modify the way your particles behave. So like I said, in 99.99% of the time, all of these settings will be more than enough to control, to offer you complete control over the particles. And maybe down the line later, in maybe 10 years, you will want to go inside the solver and change some stuff here, but really this is for future you to worry about. So don't worry about this for now. All of these solvers have a bunch of settings that you can play around with and really control the simulation. And there are really a lot of settings and things you can do with all of these parameters. Now also it's important to note that all of these kind of follow the same structure like I mentioned earlier. So let's maybe make some room. And for example, the flip solver will need a flip object. So we are going to attach this here, and the pyro solver is going to look for an object. So the first input is always going to be an object. So for the pyro, it's going to be a pyro. It's going to be a smoke object actually, so we can attach this here. Rigid body solver, most of the time is going to be RBD packed object, so all of these have object in their name. Vellum solver is going to be vellum object. So hopefully this gave you an idea. We always need an empty container. It doesn't really have to be empty all of the time and this depends for the kind of simulation that you're doing. So for example, RBD packed object will usually contain some geometry, so it doesn't need to be empty. But basically all of these solvers are looking for this object type node. So this is what I'm trying to say, and then you will also have an output usually attached to all of these, like so. And then on the right, where we have this VOPS source, some of these will also have a source to the right. So for example, for the flip solver, I can actually use the same VOPS source, so I can plug this over here and I can use an output here. And if I actually go back and reset this simulation and press play, we actually see that this is working. So if I go inside, we are actually doing a flip simulation now. So the particles are actually behaving like water, and we can see that they are also moving in the direction that we created on our velocity with the attribute VOPS. So I can play this, and we can't really see this right now. But for example, if I increase the density of the particles, so let's maybe use a lower value here, 0.05. Don't worry about any of this for now, but this is just to show you that we now have basically a particle simulation, just like that. And this is also good to demonstrate that if we learn how a basic simulation works, it will transfer over to the other kinds of simulations that we are trying to learn. So really the simplest kind of simulation for now is going to be a VOPS simulation, so this VOPS solver. And actually if I right click and step inside, so if I right click and choose allow editing of contents and step inside, we can see that this is not nearly as complicated as our flip solver. So let's go up. Again, this doesn't really matter for us at this point. It might come into play much later down the road. So let's get rid of all of this and let's go back to our simple VOPS simulation. Alright, now to show how a solver works at the most basic level, we can use the simplest version of a solver, which is a SOP solver. So if I go up, I will go ahead and get rid of this .NET and I will place this inside a simple solver like so. And let's preview this, so press R and let's step inside. So over here we have this previous frame node and we have these 4 object merges, and all of these correspond to the inputs that we have at our top level. So for example, if I plug another geometry here in our input 4, we can access this from over here. So it's just a simple object merge. We could just go ahead and delete this and I can make a new one and point it to whatever geometry I want. So this is basically what all of these are. And also note here that it says we are at the geometry level, but really we are inside a DOP network. We can see here that in our effects rain container, we are inside our solver, and then we have a DOP network over here, and then this SOP solver is actually inside this DOP network where it says dynamics here. If we go inside, we are back at the geometry level, but this is really more like a DOP network because the operations that we do are applied at every frame. Now don't worry about this too much. This is essentially just because this way we have access to our SOP level nodes. So all of the nodes that we have at the SOP level, as opposed to the DOP network where we have access only to the DOP level nodes. So it's a special kind of DOP network. Now, like I said, whatever we do inside here gets applied every frame. So this is the part that I want to talk about. We can see that even though our geometry is plugged in our first input, this object merge, so this input 1 is what we would actually want to output as well. So if I plug this here, we can see that nothing changes. All we did here basically is just bring our cube geometry from the SOP level into this solver. Now, the reason this previous frame node is special It's because instead of looking at our geometry at the SOP level, we are looking at the geometry at the previous frame. Now I know this is getting a little bit confusing, so it's easier if I just illustrate this. So let's plug this back, our previous frame, in our output, and if I add a transform node over here, and for example I would just set the translate y value here to 0.1, so we can see essentially that we just moved this cube 0.1 units upwards. This transform operation that we did here will get reapplied each frame. Now we can't really see this inside our solver, we have to go outside at the SOP level, and this is just the way the SOP solver works, and I will also get rid of this connection with our torus. But now if I play the animation, we can see that our cube is continuously moving upwards, so each frame we are reading the geometry from the previous frame and we are applying a transform value of 0.1, and as a result now our cube is flying upwards indefinitely. So we can see now that all we did here is we applied a transform node. So if I go up and if I were to do this at the SOP level and I drop down a transform and set the translate to 0.1, this will just get applied once and we wouldn't have any animation. So let's get rid of this, and in order to preview the results of the solver, I can pin the viewport, so I can click this pin over here, and this will pin the viewport at the context that we are currently at. So now no matter where I go, it's always going to show me this result over here. So now I can step inside and we can preview the animation of this SOP solver. Now usually inside a regular DOBNet we can preview the animation just fine inside the DOBNet, but when it comes to the SOP solver we have to do this kind of trick where we pin the viewport outside of the solvers. So this is just how the SOP solver works. So anyway, this is what the previous frame does. So for example, if I were to apply this transform to our input 1, we can see now that we no longer get any animation. And this is because at each frame we are reading the geometry from the SOP level as it is, without any transformations applied to it. So at each frame we are simply reading the geometry, applying the transform to it, and then at the next frame we are reading again the geometry as it is on the outside of this solver. So the changes don't accumulate in any way. And this is why this previous frame node is different, because we are reading the geometry from the SOP level at the first frame, and then we are applying the transform, and then on the next frame we are actually reading the result of this transform node and applying a new transform node on top of that. So this is the core concept of how simulations work, and don't worry if this doesn't make sense right away. In fact, this actually took me quite a while to understand, and I really encourage you to try this out yourself and do some other SOP operations inside the solver and see how they get applied when they're running in the context of a simulation, and maybe you'll get a better idea. But like I said, don't worry if you don't get this right away. So let's see how this looks with a noise instead of just a simple transform. So I will get rid of this, and actually we will need more subdivisions. So let's go up and let's get rid of this attribute VOP. We don't really need this for now. Let's go to our box and we just want to increase the subdivisions here. So I will add more axis divisions here and just give this enough geometry so we can apply some noise to this. Let's go back inside our solver and let's do this again with an attribute VOP, so we also get a little bit more practice. Let's rename this to add noise, and we will do the exact same thing that we did earlier. We will take our position, alright, and we are going to add a turbulent noise to this position. So we will generate this from our position. So let's plug this here and we will add this on top of our already existing position. And let's not forget that this turbulent noise, let's set this to 3D noise. And somehow I lost my subdivision, so let's go up. Oh, and we actually have to reset the simulations. So when this bar over here is orange, this means that we modified something in the simulation, so we usually have to go up a level and reset the simulations. So this reset simulation is going to be available for all of the DOB networks. So when I reset the simulation, now we actually have our cube with the subdivisions updated. So let's go back in our noise. And we have a 3D noise. Let's switch this to a sparse convolution noise, and we will reset our timeline. So what happens here is that the default amplitude for this noise is quite high, so each frame we are reapplying the amplitude. So if I go frame by frame, we can see that it's really doing some really huge changes here. So all we have to do really is, let's just set the amplitude to a smaller value, so we have smaller increments each frame. So I'll set the amplitude maybe to 0.1 and see what happens now. So if I play the animation, now we get something that's looking a little bit nicer, a little bit more organic. And one thing I can do here, if I want to expose a parameter, we know that we can middle mouse click on what parameter we want to expose and click promote parameter. If I want to expose all the parameters of any node at the same time, I can right click on it and go to VOPS Options and choose create input parameters. So we can see now that all of these are getting exposed at the top level. So I can make my modifications here. So we can see that we get something pretty interesting. And if I were to grab this attribute VOP, I will Control C and I will go up at the SOP level. And if I just apply this without a solver onto my box, let's take a look and play the animation. Obviously, we're not gonna get any animation at all, but at the SOP level, we could animate this amplitude. We can animate this in different ways, but I'm just gonna do it by keyframes. So at the first frame of my timeline, I'm going to hold Alt and left click on this amplitude. So we are adding a keyframe for this value 0.1, and we can see that we have a green keyframe over here on our timeline, and I will go maybe forward 72 frames and I will just increase this amplitude, so this will automatically create a new keyframe for us. And maybe I can zoom in on this timeline. So this is our second keyframe, and I can increase this value here. And now if I go back, I can play the animation and we see that we have kind of the same result, but this is not really the same. If I look at the result of the SOP Solver, and just to ignore the polygons for now, I will press W and go in my wireframe mode. We can see that this is kind of a different result. We can even see the way the points are moving. This, at least at the start, this looks a little bit more organic in its motion. And maybe we can see this better if I work with points instead. So I will just turn this box geometry into points. Let's go back to our box and let's drop a scatter node. So this will do exactly what it says. It's just going to scatter a bunch of points on the surface of the geometry. And for the options here, I will turn off relax iterations, so we get a random position for all of our points, and I will just increase the total count here to maybe 100,000. And I will plug this in my solver and also our attribute VOP. So let's go to our SOP version of this add noise and let's play our animation. So this is what we get. And let's go back to our solver and let's see what we get. So we can see that this is a little bit more, this looks a little bit nicer. It looks more like a particle simulation. It looks more fluid as opposed to our SOP version. So maybe I can template this by pressing E and I can preview them at the same time, so we can see what's happening here. We are getting different results. And for example, if I were to go inside my solver, so maybe I will add a value of 0.2 on the Y value here. If I play the simulation now, we get an even nicer result. Let's maybe increase the offset to a value of 1 and see what we get. So when I play now, we get an even more interesting result. And if I were to animate this value at the SOP level, let's go to our add noise, and again I will just add a keyframe for the offset, go forward to 75, and let's maybe just increase this offset to 5. Let's maybe take a look. Probably this is too much, so let's try an offset value of 1. Let's play. We can see that our noise sort of starts to swim vertically, so this is what's happening essentially. And this is our result as opposed to the solver version, which looks like this. So this is happening because in the SOP version we are not really accumulating the noise in any way. At each frame we are reading in the same point, so it doesn't matter if we are on frame 10 or 50, we are still bringing in just this geometry. So we are generating this noise based on the position of the points where they are over here. So we are animating the amplitude and the offset, but it's still grabbing the noise values at each frame from where it started. Whereas in the solver, if I go back, each frame we are actually creating new noise values based on their updated position. So this is why this looks a lot more organic, and this is why simulations in general can have that fluid-like motion. So that's something we can't achieve through just animating values. We have to know where the point is previously in order to achieve really organic movements. Now let's try a cooler type of noise, which is going to be a curl noise. So let's get rid of this, and I will do an attribute VOP and start fresh. And again, I will want to add on top of our position, let's drop down a curl noise. And this noise is very good at mimicking a fluid motion. So with the right values here, you can kind of get this to look like a smoke simulation. And I'll show you how this works. So I'll generate this from my position, and let's add this to our existing position, just like we did with our turbulent noise. And I will expose all of these values by right-clicking and going to VFX VOP Options and create input parameters. Let's go up, and I will reset my timeline. And by default, again, the amplitude will be way too high, so I will just drop this down, and I will just increase the step size a little bit so we don't have any flickering errors. And if I play this now, we can see that we really get a cool motion. And probably the amplitude is still too high, so I will drop this down even more, and maybe I can drop down the frequency slightly, and also maybe the roughness. Let's reduce this, and let's see what we get. Alright, so that's pretty cool. Also, I can change the way we visualize these points. So if I right click on this cube over here, I can select particles and I can select this pixel display. So now they're a little bit smaller and it kind of looks more like actual particles. So we are starting to get something really close to an actual particle simulation. And again, I can play around with this offset value as well to introduce even more variation in our noise each frame. So let's maybe set this to a value of 0.5. Probably this is too high. Or actually this is okay. Let's maybe try a value of 1. Okay, introduce even more movement. So that's fine. And now we can also combine this entire thing with a transform node, so I can also move these particles up as they get more and more noised up. So if I drop a transform, and again, let's set the translate to 0.1, and if I play the simulation, this is way too much, so let's try 0.01 instead. Alright, so now over time our particles are also moving upwards. I'll maybe change the amplitude to something even less. Let's maybe try 0.02. Alright, so this is pretty cool. So just like in VOPS, where we have to know in the back of our head that all operations are happening per point at the same time, in DOPS we have to know that each frame depends on the previous frame. So this is how we have to adjust our way of thinking when we are inside Houdini and trying to do simulations. Now we can bring this closer to the way our POPNet behaves. And I'll go up and I will untemplate the result of the scatter, so we only see the result of the solver. So the way the POPNet works, and let's do a POPNet over here and explain this better. So inside this POPNet, what this pop source is doing, it's looking at our geometry at the SOP level, and it's using this scatter node to scatter points on top of the geometry, and it's sourcing it at every frame. So to do this inside the SOP Solver, we can go ahead and we can merge this input one. So if I plug this here, it's just our points, but we can merge a new set of points each frame. So we can drop down a merge after our transform here, and we can bring in each frame new points, and we can see that they are already overlaid on top of each other. So if I reset the simulation, now we have a continuous emission of points. Maybe this is a little bit hard to see because there are a lot. So if I go up, I can reduce the scatter. Let's maybe reduce this to 1000, and let's reset the simulation. So we can see now that we have a continuous emission, and this is what the POPNet is also doing. The difference is that the POPNet is randomizing the position of the scatter each frame. So in our scatter, let's maybe turn this back into our point display. And I can also press D on my keyboard, and I can go to the geometry tab and I can increase the point size so we see this better. There is a global seed value here, and if I change this, we can randomize the position of the points. So in order to get a new random position each frame, we can map this value to our frame. So inside here I can do $F, and this will bring me my frame value. So we can see that this gives us a value of 42, and we are at frame 42. So now if I check the next frames, we are going to get a random distribution each frame. And we haven't really talked about this thing I just did here with this $F, but you can assign this $F variable to pretty much any value you want. So for example, I can also use $F here in the force total count. So now at frame 1 I will get only 1 point, and then at frame 2 I will get 2 points, and we can keep bringing in more points as our timeline progresses. And I can get rid of this expression if I hold down Ctrl Shift and left click. So now I can set this back to maybe, let's do 1000 here. Now what I wanted to show here is that now, since we have a different distribution of points at each frame, when I go inside this solver and I hit play, we can see, let's maybe turn this back into pixel display. Now we can see that we actually have something that looks really close to a normal simulation. So maybe I can now increase the total count a little bit to introduce more points. So here we have it. So let's go inside and try to make this noise a little bit cooler, maybe increase the frequency and bring back some of the roughness. And let's maybe switch the type to a simplex noise and add more offset value to this and see what we get. So maybe this is slightly cooler. Now this offset value isn't really doing a lot for us, so we can go back inside here, and this curl noise can actually take a fourth dimension for our position, which will be essentially the time. So don't really worry about this, but we can do a vector to vector 4 over here, and I will plug our position inside the vector, and I will promote this second value here, and I'll get rid of this curl noise, and let's do a new one, and I will set this to a 4D noise. So this is only available for curl noise and I think anti-aliased flow noise, but we don't really have to worry about this for now. I just want to get a slightly cooler result over here, so I'll set this to a simplex noise. Actually, I will right click and promote all of these input types and generate this from our position, and I will add this on top. So let's go up, increase the step size and reduce the amplitude. And actually let's go back, and instead of promoting our fourth value here, let's link this to our time. So all of this is basically still the same curl noise, but now it's using the time as a fourth dimension to properly evolve our noise. So now if I go up and I play the simulation, we get something a lot closer to an actual particle simulation. Now don't worry about all of this noise stuff for now. You will get used to working with noise pretty soon. So as one final thing, let's go up and let's just do an extra few steps to make this even cooler. I'll append a trail SOP here, and I want to compute the velocity. Then I can do an attribute VOP, and I can go inside and I can use this velocity to get the length of the velocity. So this is essentially the speed, and I will want to fit range this speed to some custom values, and I also want to promote all of these to the top level. And finally we will use a ramp parameter here, which is going to be a color parameter, and I will plug the result in our color. So if I go up, I can play around with the ranges of our speed, and I can also give our particles some different colors. So when they're slow, I want them to be red, and when they're fast, maybe I want them to be a sort of blue. And I can play with my values even further. And I'll press D and go to the background here, and we will set this to dark. And now if I look at the animation, we get something a little bit more interesting with more variation. So I know I went super fast just now with introducing a new node and doing a lot of operations that we are not familiar with. All of this was just to give you more of an idea of the stuff we usually do in Houdini. And this will conclude the intro to Houdini for VFX. Now I know I haven't covered rendering, but that is kind of a different topic. And honestly, rendering isn't usually where people get stuck. It's pretty straightforward. You just create a material, add some lights, and set some noise threshold in the render settings and hit render, and that's pretty much it. Now obviously we can get super fancy with materials and building shader networks. So that's why I'll probably do a different course for that. But as a beginner, you should really focus on all of the stuff that we talked about in this course. So we have to get used to the SOP tools and how to modify attributes in VOPS or VEX if you think you're better than me. And then also how DOPs work And really, when it comes to VOPS, this is where we have to branch out into the different solvers that Houdini provides. So I will have a separate course for learning the basics of each solver. So there's going to be intro to Flip, intro to Pyro, intro to Vellum. So we have to understand how all of these work and the differences between them, and then also really get comfortable with using VOPS. And on that note, I want to show you one final thing, is that if we have this torus over here, and if I drop this into the popnet, so we can see that we scatter some points, and earlier we created a velocity attribute outside of this popnet, but if I go inside, I can actually drop here a geometry VOP, and I will place it below our source. So this geometry VOP is essentially exactly like an attribute VOP. So if we step inside, we have the exact same layout and we have all of the nodes that we have in VOPS. But again, the difference here is that this gets applied at each frame. So for example, I can do a constant value and I will set this to be a tree float. So exactly the same thing that we did earlier. Let's maybe use a value of 1 on the Y. And if I plug this into the velocity and reset the simulation, we can see that our points are moving upwards. So this is great. So far this is not any different from the way we did it earlier when we assign this velocity value at the SOP level. And this is because each frame we are just adding the same value to our points. But for example, if I were to add this value on top of the velocity that we already have, so if I plug the V inside our V here and I add this constant value on top of the velocity, if I play the simulation now, we can see that after only a few frames our particles start to get crazy. And this is because we are also adding the velocity that already existed in the previous frame. So at frame 1 we are going to add a velocity of 0, 1 and 0. Then on the second frame, this set of points that moved will already have this 0, 1, 0 velocity, and we are adding on top of that. So on the second frame, our first set of points will have a velocity of 0, 2 and 0. Then on the third frame, we are going to keep adding on top of what we have. So this is why only in a few frames, since this is an accumulative process, because this is an add operation, we keep adding more and more on top of the vector that we already have. So we can see that after a while the vectors get really huge. So this is going to take a while to get used to in terms of what VOPS operations do, but I wanted to show you that you do have this attribute VOP. It's called a geometry VOP in a VOP network, but it's still just an attribute VOP. So we have access to this, and in fact most of the simulations, especially particle simulations, I rely almost entirely on doing stuff inside the geometry VOP. So if we learn how to use the VOPs at the SOP level, it's really gonna come in handy when we try to do simulations as well inside a VOP network. So that's all I wanted to say. I hope you enjoyed this course and that you got a better idea on how Houdini operates. And don't worry if some stuff didn't make sense. As I was starting out, a lot of things I just kind of understood, and that was actually enough to do some pretty cool stuff, and only much later I really actually understood what's happening. So I'm trying to say that you don't have to really understand this stuff right away, as long as you kind of got an idea of how stuff works, and really everything only starts to make sense if you actually get your hands dirty and do the stuff in Houdini yourself. So it's not really enough to just watch videos and get the information. You actually have to be inside of Houdini and you have to lay down nodes and try things out and fail a lot of times really, until eventually stuff starts to click. So that's all for now. Hopefully we can see each other again in a new tutorial.